Hello everybody, thank you for letting me take a moment of your time. My name is Flemming and I work as manager for our package IP solution in Comcores. I have the opportunity to introduce Comcores and talk about time-sensitive network and how TSN contributes to deterministic transmission of critical information.
Today I have 4 bullets on the agenda. First, I'll give a short introduction to Comcores. Second, I will talk about the key reason for why we should use time-sensitive network instead of regular Ethernet. Third, I'll talk about what TSN is and walk through a selected set of features that are introduced with TSN. And last, I'll give an example of how we at Comcores can help you with easier and more seamless deployment of TSN.
Comcores' primary business and mission is to provide quality IP component and solutions for ASICs, FPGA, and solution vendors. An important factor to us is to reduce the overall cost, risk, and time to market for our customers. Comcores are located in Copenhagen, Denmark, and have a development site in Poland as well. We are working within 3 technology areas as shown on the slide. On the left, we have the chip-to-chip interface, where we are market leading within JST 204, where we have solution for both B and C version and the upcoming D standard. In this group, we also have other chip-to-chip interfaces like Interlaken. The second technology area we are working within is wireless fronthaul and O-RAN, where we have multiple components for CBRI, eCBRI, radio or Ethernet to support this. The last technology area where we are working with is Ethernet, both with and without TSN support. We have various components like PCS, MAC, and switches, all ranging from 10 megabit to 100 gigabit line speed. We have also hardware implemented security IPs like MACsec. As a part of our offering to both TSN and fronthaul, are we also working with the timing solutions based on IEEE 1588 PGP. The next topic I would like to speak about is why use time-sensitive network. What benefit does TSN bring that cannot be achieved with regular Ethernet? There can be many different requirements and reasons to use TSN. In general, is the overall goal with TSN to provide deterministic guarantees for quality of service as well as reliability in a switched network based on Ethernet. By adding TSN to your infrastructure network, is it possible to have one converged network that can both cover OT and IT network. It is, for example, possible to guarantee latencies from a critical sensor or certain bandwidth from a video source on a factory floor while having regular IT traffic running on the same network. So the need for separating these two networks is no longer required due to your critical real-time systems will not be impacted by the background traffic. Compatibility is also a big important for using TSN. TSN is not driven by a single big vendor, but have contribution from many vendors with the collaboration through IEEE. This ensures that equipment from different vendors can coexist in the same network due to the effort in standardization and plugfests. The standardization work for profiles for different vertical markets also ensure that there are consistent feature support between equipment from different vendors for a given use case. The last item on my list is kind of contradicting the previous one. Despite all the work in regards to standardization of the different profiles in TSN, does it not prevent anyone from designing their network with exactly the desired TSN features they need for their use case? This makes, of course, most sense in closed environment where all network elements are in control. One would probably ask, why should anyone do that? And the quick answer would be that this will simplify the solution, minimize the footprint of a chip if unused features can be left out.
In the next section, I will talk about what time-sensitive network is and highlight some of the key features that give the guaranteed latency, bandwidth, and reliability. TSN originates from the audio-video broadcasting industry and was transitioned to TSN approximately 10 years ago, where the TSN task group were founded by IEEE. TSN is not a single standard, but more a toolset consisting of many standards that are published as amendment to the IEEE 802.1q standard, also what we know in the daily wording as VLAN. Some of those are published but many are still in draft, so despite for the work on TSN was started a decade ago, This is still a work in progress. There are two parts of the standardization going on. One part is for the different TSN components shown in the bottom part of the picture. The upper part shows the TSN profile for the different vertical markets, like automotive, industrial automation, wireless fronthaul, and others. The components are focused on four main areas. Time synchronization shown on the upper left corner, where TSN has its own PCB IEEE 1588 profile. The lower left corner focused on the features like traffic shaping to support guaranteed latencies and bandwidth. Some of those require time synchronization, but not all. So despite for it's called time-sensitive network, are there no requirement for time synchronization? It depends fully on which features that are needed to be supported. The upper right standards are focused on reliability, both in terms of security of reliable time synchronization in the network, but also in terms of securing reliability for transmission and receiving the individual Ethernet package. The huge pile of standards in the lower right corner is focused on resource management, how to collect requirements and capabilities from the individual elements in the network, how to set up and configure the elements according to the requirements, how to collect network statistics, to real-time monitoring of the network, and adjust performance to new and changing requirements.
As shown on the previous slide, are there many more features in TSN than possible to cover in this presentation. So I have selected a few of the most common used that also illustrates how requirements to latency and bandwidth can be fulfilled with TSN features. The first feature I would like to talk about is 802.1 QAV credit-based shaper. One of the benefits with the credit-based shaper is that it spreads out frame transmission and reduces bursting of class-based traffic. It also gives the possibility to prioritize bandwidth between different traffic classes. In the illustration shows the blue and orange line that transmission of a traffic class is only possible if the credit for a given class is positive when the transmission is ready to start. After the first blue and orange package is transmitted, where the arrow point on the picture is credited from both class A and B negative, so no transmission from either of those traffic classes can start. They need to wait. This gives room for the best effort traffic to be transmitted. Time synchronization is not needed for the credit-based shaper. So if this can fulfill the TSN requirement for a network, can the whole time synchronization of the network elements be avoided. The next feature to mention is the 802.1 QBV time-aware shaper. This is just as common used as the credit-based shaper. As the name indicates, does the shaper rely on timing. It works in a way that it divides the time into repetitive periods where gates for the different traffic classes can be opened or closed during the period to allow priority traffic to be transmitted at a certain time. This eliminates jitter and unwanted delay through the network by allocating time slots to the traffic class of service. This gives a very predictable and deterministic behavior of the traffic. If we use the analogy to our daily drive traffic, would a synchronized network with time-aware shapers be able to guarantee a green wave through a city in the rush hour for a prioritized emergency vehicle? The last feature in relation to latency and bandwidth I want to talk about is the 802.1 QBU frame preemption. The idea with frame preemption is that high prioritized frame classified as express packages can interrupt and put ongoing frame transmission on hold, while the express package will be sent. After all, the preemptible frame continues the transmission. Downside of this is that frame preemption adds overhead to the bandwidth due to insertion of a trailer for the first part of the preemptible frame, as well as a header for the second part. The main motivation for using frame preemption is to minimize latency for express packages in the network, due to they do not need to wait for an ongoing transmission to finish before it can be transmitted. The line rate has an impact on the efficiency of frame preemption, due to the time spent on the wire or fiber for a frame is significantly lower in a network running at example 25 gigabit instead of 10 megabit. So the efficiency are higher with lower speed and decline when the network speed grows. Reliability can be a strong requirement for TSN network. 802.1cb frame replication and elimination gives to a large degree guarantee that the frame will arrive at the destination in the network. In TSN, a network consists of three key elements. The talker that transmits traffic to a listener. The talker can, for example, be a sensor or actuator. The listener can, as an example, be some sort of controller that needs information from the talker. In between the talker and the listener, the network have various TSN bridges. A bridge can be compared with a switch in a traditional Ethernet network. In the example on the left are frame replication and elimination implemented in the bridge. So when the frame arrives at the first bridge from the talker, will it be replicated and traverse in two different routes in the network. Again, will the replication be eliminated on the last bridge before only one copy of the frame will be transmitted to the listener. In the example on the right are frames replicated in the talker and eliminated in the listener. This removed the single point of failure that both the first and the last bridge are in the left illustration. Besides for the reliability, frame replication also provide lower latency, due to latency will always be equal the fastest of the two routes in the network. With my last bullet on the agenda, would I like to elaborate on how Comcores in various ways can help enabling TSN. We have in principle three ways we typically collaborate with customers. These are illustrated in this picture with the famous Lego bricks. Most of our offerings can be delivered for both FPGA and ASICs as a target. Performance can vary depending on the target. First of all, can we deliver standalone IP components or bundle with other IPs? Second, can we deliver subsystems with IP components that are pre-integrated as what we call package IP solutions? I will on the next slide elaborate a bit more with an example of this. Third, can we deliver more complete solutions including software? These will typically be running on some kind of FPGA platform, either to demonstrate functionality or be running on the end hardware platform as the final product. The picture here illustrates a full TSN switch system including software, with PCB stack running on the embedded Linux system. This could be delivered as a full solution running on a customized hardware platform. Alternative, could we also deliver the IP in the lower right corner that are surrounded by the dotted line as a package IP solution. The motivation behind the package IP solution is that our customer will reduce the complexity and the effort in integration, and can treat this as one big IP they can combine with other IPs of their own or third-party IPs. This enables them to tailor the solution to exactly their requirement with lower effort and still have full control over all blocks in the design. Thank you everyone for listening to this presentation about time-sensitive network.